What if I told you we might not need rockets to reach space anymore? Imagine stepping into an elevator, pressing a button, and rising 62,000 miles above Earth into orbit. It sounds like science fiction, but scientists say it's actually possible. In this video, we're breaking down the real concept of the space elevator, how it would work, what materials could make it possible, and whether we're closer to building it than you think. What even is a space elevator? Imagine a single incredibly long cable anchored firmly to the Earth's equator. This cable isn't just dangling. It stretches straight up, far beyond the highest satellites we currently have, reaching past geostationary orbit. And at the very top, it's attached to a massive counterweight that floats in space. The purpose of this counterweight is crucial. It keeps the cable taut and stable, counteracting the pull of gravity so the structure doesn't collapse back down to Earth. Now picture a climber, a kind of futuristic elevator car, slowly ascending this cable. This climber could carry people, supplies, or even large spacecraft components, all the way from the Earth's surface into orbit, completely eliminating the need for conventional rocket fuel. Unlike rockets, which have to overcome gravity and accelerate to enormous speeds in one go, this system would allow a steady, continuous journey into space. This isn't a brand new idea. The concept dates back to 1895, when the Russian scientist Konstantin Tsiolkovsky, inspired by the Eiffel Tower in Paris, imagined a tower so tall it could reach into space. He envisioned it as a way to transport people and goods without rockets. Later, in 1960, Yuri Artsutanov formalized the idea and suggested the use of a counterweight beyond geostationary orbit to stabilize the cable, making the concept more scientifically viable. By the 1970s, the idea was being seriously studied by engineers and physicists as a potential way to revolutionize space travel. Why rockets are a problem worth solving. Right now, getting 1 kilogram of cargo to low Earth orbit costs somewhere between $1,500 and $10,000 depending on the rocket. That's not a typo. Every satellite, every space station resupply mission, every astronaut. The cost is dominated by fuel and engineering needed to fight Earth's gravity for the first few minutes of flight. The space shuttle era cost NASA roughly $54,000 per kilogram. SpaceX's Falcon 9 brought that down dramatically, and Starship promises to go even lower. But even at $100 per kilogram, SpaceX's aggressive target, a space elevator could theoretically do it for $10 to $100 per kilogram at scale. We're talking about slashing launch costs by a factor of 100 or more. That changes everything. Space tourism isn't just for billionaires. Asteroid mining becomes economical. Permanent moon colonies become logistically feasible rather than distant fantasy. The carbon nanotube problem. So what's the catch? The cable. A space elevator cable needs to be under enormous tension, supporting its own weight across 100,000 kilometers, while holding cargo loads on top of that. Steel is way too heavy. Kevlar isn't strong enough. Carbon nanotubes are the material scientists keep coming back to. They're cylindrical molecules made of carbon atoms arranged in a hexagonal lattice, extraordinarily strong. Roughly 100 times stronger than steel at 1/6 the weight. In theory, they're the only known material with the specific strength needed to make a space elevator cable work. The problem is we can't make them long enough, yet. Current manufacturing produces nanotubes measured in centimeters. We need ones woven into a cable hundreds of thousands of kilometers long. Research is pushing forward, and the science is advancing faster than most people realize. Where would you build it? Location matters enormously. The anchor point needs to be on or near the equator because that's where the geometry of geostationary orbit works. The counterweight must stay fixed above the same point on Earth as the planet rotates. The ocean is the preferred site because it avoids sovereignty disputes between nations, and a floating platform can be slowly repositioned to dodge space debris. Ecuador, Colombia, and the Central Pacific are top candidates. The counterweight at the other end, roughly 36,000 kilometers up and well beyond geostationary orbit, could be a captured asteroid or a purpose-built station. The whole system stays taut because the counterweight wants to fly outward due to centrifugal force while gravity pulls the cable down. They balance each other perfectly. How would the climber actually work? The elevator car, called a climber, would grip the cable and work its way up using electromagnetic or mechanical drive systems. Speed estimates fall between 200 and 300 kilometers per hour, meaning a trip to geostationary orbit takes about a week. That sounds slow, but when you're not burning rocket fuel every second of the journey, slow and steady isn't a problem. It's a feature. Power is one of the biggest engineering challenges. The climber can't carry enough fuel for the whole trip. The leading solution is beaming power up from the ground using high-powered lasers or microwave transmitters, absorbed by photovoltaic cells on the climber itself. No fuel, no combustion, no explosion. Just electricity and physics doing exactly what they're supposed to do. The real dangers you haven't thought about. Space is not a friendly place for a 100,000-kilometer cable. The biggest threat is space debris. Tens of thousands of pieces of junk orbit Earth right now, and a high-speed fragment hitting a taut cable would be catastrophic. The floating anchor platform helps here. You could move it slowly to dodge predicted debris paths. There's also weather and atmospheric drag on the lower cable. Storms, lightning strikes, and wind loads all become serious engineering problems. Radiation is another concern. The cable and climbers will pass through the Van Allen radiation belts, intense bands of charged particles that degrade materials and electronics over time. And then there's the geopolitical problem. Whoever controls the space elevator controls access to orbit. That's a level of infrastructure power that makes today's internet infrastructure disputes look minor. Who is actually working on this? This isn't purely theoretical anymore. Japan's Obayashi Corporation announced in 2012 that they intend to build a space elevator by 2050, and they've been quietly working toward it since. NASA has funded research into space elevator concepts and carbon nanotube development. The International Space Elevator Consortium, yes, a real organization, has been advocating and coordinating research since 2008, holding annual conferences and publishing technical papers. There's also a competitive angle. China has publicly expressed interest in space elevator technology as part of its long-term space ambitions. When multiple superpowers and major corporations take something seriously, it usually means the underlying physics makes sense and the engineering challenges, while massive, look solvable within a few decades. What it would actually change. If a space elevator gets built, it rewrites the economics of everything beyond Earth's atmosphere. Right now, the cost of reaching orbit acts as a hard ceiling on human ambition in space. Satellites become cheaper to deploy and replace. Space-based solar power, collecting energy in orbit and beaming it to Earth, suddenly becomes economically viable. We could move heavy industry off Earth and into orbit, reducing pollution on the surface. The Moon and Mars become realistic destinations for permanent human settlement rather than distant dreams. And it changes who can access space, not just billion-dollar agencies or ultra-wealthy companies, but eventually universities, startups, and smaller nations. Anyone with a payload and a ticket. The future of space travel might not be louder rockets. It could be a quiet ride straight to the stars. If this blew your mind, hit like and subscribe for more futuristic breakthroughs. And watch the next video to see which space technologies could become reality in our lifetime.